Hello and welcome to another episode of Fun Times in Statistics. Today we're going to be talking about Chapter 6, where we'll be covering random variables and probability models. We will not be doing all of the probability models you see in this chapter because some of them are continuous models, and I'll be saving them for when we talk about continuous models. So if you've been following along with the book, you'll notice there are a few things I skip, specifically the exponential and the Poisson distribution. So if you see those, just save those for later. They're coming up in Chapter 7 because that's where I feel like they belong. Oh well. First off, we need to define what a random variable is. A variable whose value is based on the outcome of a random event is called a random variable. So be thinking back to when we were rolling dice or flipping a coin. Those would be examples of random variables if you counted things from those events, like the number of times you get a head if you flip the coin 5 times would be an example of a random variable. If you can list out all the possible outcomes, a random variable is called discrete. If a random variable can take on any value between two distinct values, it's called continuous. So if you're thinking any value, how finite and small can that be? So be thinking like fractions of fractions and parts of parts. A good example of a continuous random variable would be height, because although you know that height is somewhere probably between like 0 and 8 feet, you could take on any value in that range down to finite, like small inches of inches and feet of feet. So most people round their height and don't use the exact value, so it looks continuous. Example of discrete would be like the one I just did for my random variable, where I was counting the number of heads I got when I flipped the coin 5 times. Other examples of discrete might be the number of calls you had dropped from your phone in the last month. That's luckily gotten better. Maybe for continuous, you could think of things like, oh, the miles per gallon of my car. It could be anything in a certain range. Or maybe the number of hours you've spent studying for this course. The reason we're going to treat that as continuous is because you can spend minutes on it as well, which are parts of hours. So be thinking if it has parts, it could look continuous. Can I get small fractional pieces? That should help you. Okay. So as you look at these random variables, you might be thinking, okay, I know what they are. I know their values. How often do they occur? And that's exactly how we build a probability model. This is also called a probability distribution because distributions do two things. They tell you what value and how often. So when you have this, you have what's called a probability model. I'm going to show you an example of one in a minute. The other thing is we also talk about probability models in terms of some common themes, in particular the mean. So we can find that on a probability model by doing the following. It's called the expected value in this case because it's the value you expect to get on average or in the long run using the law of large numbers. As you look at this, it's written as E of x, since because there is lots of variables floating around, whereas x is a random variable, so we read this as the expected value of x is the sum of all the possible outcomes. So think of x as an outcome, times the probability of that outcome, which I'm not writing. Live with it. So it's not only accounting for what the outcomes were, but how often they occurred together in making your mean. And this makes sense because if you know how often something happens, its likelihood or probability, and what that value is, you can combine it to figure out what's happening on average, expected value. So I'm hoping you remember the mean, or mu, is the mean of a population from earlier in the semester. So let's see how to do some of this. So here is a probability model for you. The reason this is a probability model because it gives you the outcome, the payable value, and the probability that that outcome occurs. So you also might be thinking about this as just like, oh, well, then why do I need this column? Well, you really don't to form the probability model. These are the two that you need. This is just this first column is a lovely note about, why. Anyway, so this is for a life insurance policy. Clearly, certain ones are worth more than the others, and certain ones are more rare than the others, so you don't end up paying out and things like that. So you might look at this and be like, well, how much do we expect this policy to cost us each year? Because that's exactly how they're going to calculate your premiums. Well, you can do that using the expected value. So here we are using that probability model for life insurance that we showed last slide. We want to find the expected annual payout on the policy, or the expected value. this will tell you what your payments look like. So you take the value in particular. So I'm looking at, let me just use a light color here. I take the amount times its probability, amount times its probability, amount times its probability, and then you add them all together, and that will give you a value you expect to get. So we expect the insurance company will end up paying out about $200 per year in policies. They can use that to figure out, hey, what should we charge for our premium to cover our costs? Next up, we have the standard deviation, or spread of the discrete random variable. So I'm hoping you notice this is following a theme. Oh, I want to find the mean and the spread so I can figure out what's happening on average and what the typical values are that I see in my distribution. So here you do just like when we did standard deviation. When was this? Chapter 3. Wow, it's been a while. So you look at this and you're like, oh, distance from the mean or deviation from the mean times the likelihood or probability. We used to average this, and then we add them all up to account for all variation, and I take the square root to undo the size of the square to get the standard deviation. Whew. Doing this by hand is a disaster. You don't want to do it. Okay. But here's how you do it, because I'm the devil. I figured you want to see an example. So notice we found the mean previously. It was $200. So the first thing we want to do is we want to find the deviation. So this is taking each x value and subtracting the expected value of v, or the mean, which was $200. So you look right here, and I'm taking that $1,000, the first payout, subtracting 200, coming up with this value, subtracting 200, coming up with that value, subtracting 200, coming out with a negative. Remember, we're squaring, so that's not going to matter. And then each of these gets placed next to its probability squared. So this isn't too bad. These numbers can get big very quickly if you have large values present. And then the last thing you're going to do after you add these all together is you're going to take the square root. I highly suggest that you take a minute to take your calculator and make sure that you can produce all these calculations correctly to make sure you're getting the correct values, and you know how to do it on your calculator for when you need it. Doing this on Minitab is a freaking disaster, but yeah. Anyway, it's still doable. I will show you how, but you know, once this gets above 5, you don't want to do it by hand, pretty much, ever. Sorry, that was probably loud on the microphone. I apologize. Okay, let's do an example. Suppose the probability a customer is purchasing 0, 1, or 2 books at a bookstore is 0.2, 0.4, or 0.4 respectively. What's the expected number of books a customer will purchase? What do we expect? We expect the mean. We're going to do a mean. And then what's the standard deviation? So similarly, I'm going to first find the mean and then come up with the variance and then take its square root to get the standard deviation. This is just like the previous example, only with slightly different values. Okay, so the first thing I want to do is calculate the mean. So I'm going to take each value, multiply it by its probability, and then add them all together. Ta-da! 1.2. So now I need to find the deviations, square them, and multiply by the probability. So I subtract the 0, the 1, and the 2 from, the 1.2 from 0, 1, and 2. That's the deviations, and square them. So this is the deviations right here. And then multiply them by their respective probabilities. Add all those values together, and that comes up with 0.56. Then you're going to take the square root of that to get the standard deviation. So if you're paying attention, there's a lot of work in here. Here's the mean, and then here's the standard deviation. So when you're looking for answers, there it is. I really consider all this work your answer, but you know, if you want to know which thing to put in the box, there you go. Anyway, so let's talk about manipulating random variables a little bit. Now that we know what they are and how to find expected values on them, we want to see what happens with changing expectations. So imagine C is just a constant, so it's a number. If we want to add or subtract that to our random variable x, you would do the same thing to its mean, and it would have no effect on the standard deviation or the variance. So here's what I want you to picture. You have a data set, you've done a bunch of measurements, so you're, I don't know, what could you produce? Say you produce hula hoops, and you measure the diameter of all of them to make sure you're not making ones that are different sizes, because evidently hula hoops have standards. And then you find the mean, you find the variance, and the standard deviation, and you're happy. But then you realize that your ruler was a little screwed up, and somebody had been measuring from the 1-inch mark instead of the 0 mark. So you need to add 1 inch, aka add a constant, to all of your hula hoops. So what would happen to your mean? If I'm adding 1 to everybody, on average, oh, I go up by 1, and that's exactly what this says. You know, to find the mean when I have to add or subtract something to my random variable, it's the same as finding the mean and then adding or subtracting something. And here's where this gets interesting. Adding or subtracting something doesn't change the variance or the standard deviation. Remember, standard deviation is average distance from the mean. But if everybody is, you know, going up by an inch, then their average distance isn't changing. They're just moving over in the number line. Their distance from each other is still the same. So the standard deviation and the variance are absolutely not affected by this, which is why this doesn't change. Yeah? Okay. How about multiplying by a constant? This is something like conversion. So say you did your measurements for your hula hoops in inches, but you have a foreign manufacturer who wants to sell these hula hoops, but they want them in centimeters. So you figure out what that conversion factor is, and then you multiply all your variables by that conversion factor. That's your value of A, so that your measurements are now in centimeters. What happens to your mean? Well, if everybody's being multiplied by something, then the mean is just multiplied by that something. What happens to your variance? Well, variance has squaring in its process. You end up with an A squared times it. And then since you're squaring and then rooting, when you're looking at the standard deviation, you end up with an absolute value. And the reason this happens is because when you do the absolute value of a square, you end up with something that's always positive, because squaring first makes it positive, and then rooting, oh, I'm still going to get a positive result. So even if A was negative originally, when I square root that square, I get something positive. This is not the same as just getting A. So if somebody ever told you that roots and squares don't quite undo each other, it's because of this process. Because if you take -4 and square it, you get 16, but then when you take the square root of 16, you get 4. Makes things be positive. Fun facts. Let's see how to use this with our life insurance policy example. So the addition rule, oh crap. I'm not recording that last slide again because it took me forever to get through that. If you want to add two random variables together and do their mean, it's the same as doing their means added. If you want to add or subtract their variances and standard deviations, oh my gosh, excuse me, you just end up with them added. And I really want you to pay attention to this. Notice this says plus or minus, and you just get plus. Because when it comes to adding in another variable, you can only increase in variation or spread. You can never decrease in spread because this is a distance. So it's always positive. That was supposed to be an always. It doesn't look like words though. Print it. Why? Why? Always plus, even if it's doing subtraction, so be careful. And that's also true for the standard deviation. That will always be a plus, even if what you're doing here is a minus. So just keep that in mind, because I can only add variation in by adding in another variable. The idea that it would reduce the amount of spread you're seeing is just crazy. Doesn't make any sense. Anyway, here's the example I thought I was on, which is the life insurance policy. So we already found out that the mean payout we expect is $200 with a variance of $14,960,000. I'm not reading that number again. If the payout amount is doubled, what's the new expected value variance? So I'm doubling everything. I'm multiplying by 2. So you would expect it to double on average for the mean, and it should increase your variation by 4 because it's sorry, I had a bit of an asthma issue. And so it's 4 times as variable as previous because I'm doubling my policy. Now, I want you to notice the difference between that and having 2 policies, which I'm doing on the next slide. So if I have 2 policies, my mean is the same. Yeah, I'm adding 2 of them together. But my variance is a lot smaller, and this is interesting. So doubling your policy actually costs more and has more variability than just having 2 people be present. So this is a very strange thing that happens when it comes to calculating probabilities and variances. It's a little weird. Anyway, so you should think about that if you're interested in insurance. It definitely changes things. It's a little strange. Right. Bernoulli trials. Sometimes you're going to want to repeat a process over and over again, like flipping a coin, or doing multiple births, or maybe you want to produce lots and lots and lots of items because you're interested in manufacturing. The point is, you're not always doing something just once. When you have that, you have a Bernoulli trial, as long as there are only 2 outcomes to your trial. So you have something that you consider a success and something that's considered a failure. We call the probability of success P, and then the probability of failure Q. And we need all the trials to be independent. Examples of Bernoulli trials include tossing a coin, tossing a coin, collecting yes or no responses from a survey, or shooting free throws from basketball. Those of you who are interested in marketing, the yes or no responses are totally your thing. All right, so when you're using Bernoulli trials to develop probability models, we really require that they're independent because you don't want any dependence between your trials. The other thing we need to be careful about is something called the 10% condition. As long as the trial or number of sample size is less than 10% of the population, we won't have any issues with it oversampling or creating chaos, basically. We want it to be under 10%. More than often than not, we'll be doing small samples and this won't matter at all. Especially if you're doing something like the US population, having 1,000 people is totally not 10%. So you're good. And as long as you have independence, we're good. We're ready to go. I know you might think that why am I talking about this 10% and independence issue? They are very important as you proceed forward. One of the biggest complaints that I get from employers is that students will try to do things using a certain distribution and they don't check to see if they should. So it's kind of like the lesson from Jurassic Park. Just because you can doesn't mean you should. You should probably check if you can in the first place. Or I got that totally backwards. Dinosaurs. Don't kill the world. Got it. Anyway, the first model we're going to look at is what's called the uniform model. The uniform model is a lot like the dice. So if I have 6 options and they're all equally the same in probability, then my probability is just one out of the possibilities. So this is called the most discrete possible in the world. If you're wondering what it looks like a big brick. So if you have your distribution like this, and here's like 1, 2, 3, 4, 5, 6, here. I don't know why I'm insisting on doing this in purple. Here's 1/6. And I gotta make little bricks for all these. They're all the same probability, so they're all the same height. And that's also one thing that's unique about probability distributions, is that when I talk about calculating probability now, it's in terms of area. So if I want to know what's the probability I get a 1 or a 2, that's the options in this brick and this brick. So 2/6. Because there are 2 bricks. It's area now, which is weird, but it's totally what's going on. Because when I calculate probabilities, I'm doing outcome value times probability, height. So width times height makes area. Interesting, right? Let's do an example to make sure we're all on the same page. So let's look at a customer satisfaction survey. A cable provider wants to contact their customers, to see if they're satisfied with their new digital TV service. If all customers are in the 452 phone exchange, this is just so hard to read. I'm sorry. There are 10,000 possible numbers from 452 to 00000. So what I'm saying is like how you have area code and then you have the second 3 numbers. That's actually called your exchange code, in case no one ever told you that. And there's 10,000 possibilities. So the phone numbers look like 452 dash bunch of zeros to 452 dash bunch of 9s. So it's kind of like you're in the the 837 area code. That's one of the ones in middle. Sorry, if you're in the 989 area code, it's one of the ones in Midland. The ones for Northwood are in the 837 exchange code. So if you wanted those, you would have 837, not 452. Fun facts. Now you know the name of that. Hopefully that doesn't stay in your brain because that's weird. Okay, what's the probability model that should be used for selecting a single number? What's the probability that the number selected will be an even number? What's the probability the number selected will end in 000? That's a fun one. Let's look at these. So if you're thinking like, oh, well, all my numbers are treated equally, they're all equally likely to be selected. You're right. This looks uniform. All the numbers are equally likely. That's why this is uniform. What's the probability it's even? You don't actually have to use the uniform distribution to calculate this because, well, half the numbers are even, so it should be half. This makes sense. What's the probability that the selected number will end in 000? This one's a little bit harder. So this looks like 4, what was it, 52, 82? I'd go look back, but I don't care enough to bother. That and this will make me have to re-record this slide. Did you know that? It's a little obnoxious. It's 452. Sorry, I have my notes in front of me. Dash something, and then 0, 0, 0. So what are the options here? Well, there's 10 options. There's 0, there's 1, there's 2, there's 3, there's 4, there's 5, there's 6, there's 7, there's 8, there's 9. That's actually 10 options, not 9 options. So I have 10 options out of 10,000 options, which is 0.001. That's how we figured that out. And that's exactly how you do the uniform. How many options are there out of how many possible options? It's very simple, just like with the dice. 2 out of 6. Let's look at another probability model that might be a little bit more interesting. The geometric model. I like to call the geometric model the stubborn model because it's repeat a process until you achieve your first success. So this is like I'm standing at the hoop and I'm going to throw my basketball through the hoop until I actually succeed, or at the hoop, not through it. Because if you threw it through it, I mean, what was your success? I don't know. It's also called the stubborn salesman because this is usually used to track to see how many failed sales you have until you hit a success, which is an interesting model. So when you look at this, our probability of success is P, our failure probability is Q, which is 1 minus P, and then we want to count until we hit our first success, so that's our random variable, our X. So X is equal to little x will be the count we succeed on, so this is like maybe 4, so then you have 3 failures until you hit your first success on that last try. The expected value for this, or the mean, is 1 over P, because if you succeed 1/4 of the time, it should take you 4 tries to get there. The standard deviation is a little bit more difficult to understand, so I'm going to skip that because we don't really use it for anything. But that's what the geometric model looks like. Let's do an example. So suppose, oh crap, this is the salesman one. I thought I was doing a different one. I mean, I totally expected this, and I definitely lied to you guys. No, just kidding. I have no idea. I thought I had a different one. It's fine. Anyway, so a salesman normally closes a sale on 80% of his presentations. Assuming the presentations are independent because they are different individuals, what model should be used to determine the probability that he closes his first presentation on the 4th attempt? So we're talking about his first success, and it's on the 4th try. This looks very much like a geometric model. What's the probability that he closes his first presentation on the 4th attempt? So be thinking fail, 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 success. So it happens here and only here as his first success. It didn't happen in less than 4. It's on the 4th time. So what does this look like? Wow, that didn't come out exactly like I thought it would. What model should it be? Hey, we already discussed that. It's geometric. What's the probability that he closes his first presentation on the 4th attempt? Well, we write that as, I want to succeed on the 4th try because that's what X is. So I have 3 failures, so that's where so failure probability is 20% because he succeeds 80% of the time. So he has 3 failures, failure, 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 and then success. And that's where that cube is coming from. It's 0.2 times 0.2 times 0.2, and then the 0.8 for his success. If you multiply that all out, you get 0.000, sorry, too many zeros there, and then 64. Remember, probabilities are decimals, so you should be looking like this, not talking about percentages unless you're asked to convert it to a percent. Let's talk about the binomial model. So the binomial is a little bit like the geometric, but not at all. So the binomial is usually a little bit confused with the geometric, but it's not the stubbornness model. It doesn't have a fun name model, but it is more common. We use this to predict the number of successes in a fixed number of Bernoulli trials. So this is more like, okay, I'm standing at the hoop and I want to make 3 out of 5 of my baskets. I know how many times I'm going to try, and I want to keep track of my number of successes or my likelihood of success. So it's very different because you have only a certain number of times you're going to try. You're not going to keep repeating until you succeed. So, and then you're counting your successes within that number. So you know how many times you're going to try. That's how it is. And this has a funky ass model. Anyway, so N is the number of times you're going to try, P is your success as always, Q is your failure as always, and X is the number of successes in the N trials. So if you're looking at this and trying to think, oh my gosh, this looks kind of complicated. Well, let me do like just a quick little example down below. Say you want to flip a coin 3 times and you want to get 2 heads. So you have a couple options. You could end up with head, head, tails, tails, head, head. I'm missing one. Oh, head, tails, head. Those are your 3 ways that this could happen. Okay, and what does this look like? Well, I have 2 heads, and that happens 50% of the time. And then I have 1 tail 50% of the time. I should have chose something else. So these are my successes. This is my failure. Yeah. So it's my number of successes, P squared, times my 1 failure, which is Q. And there are 3 ways this can happen, so I need a number here for the 3 ways this could happen. So probability times number of ways it could happen. And that's exactly what this lines up with. There's my ways it could happen, there's its probability, and there, sorry, that's the probability of success, and there's the probability of failure, which is whatever's left over after your number of trials of success are done. And this is a little complicated. We're going to use Minitab to calculate this most of the time. Your calculator will do this if you have a complicated calculator that can do what's called a combination, which is what the name of this is. Combination. So a combination is the number of ways you can arrange X in n tries. Arrange X in n spaces, really. So if you look over here with my heads and tails example, I was like, oh, well, I want to flip it 3 times. That's my spaces, 3 spaces. And then I have 2 successes because I want 2 heads and 3 tries. And this differs depending on the number of times you're going to try. So if you want 6 heads in 10 tries, this gets bigger because there's more options. Even if you're just doing 1 success out of 5, it gets big really quickly. Yep. And just so you know, this little exclamation point guy is called a factorial. His formula is n times n minus 1 times n minus 2, and then you repeat until you hit 1. So for instance, if you wanted to do 5 factorial, that would be 5 times 4 times 3 times 2 times 1. And if you calculate that, that's 120. Fun facts, in case you've never seen him before. Okay. The other thing to keep in mind with the Bernoulli is that his mean, and this is super important, so put hearts and stars on this one, and standard deviation are always the following. The mean is always the number of trials times your probability of success. So if you know you're correct 1/10 of the time, and you're going to try 10 times, you should have 1 success, you know, n times p. And then the standard deviation is just like, hey, I want to count for not just success, but also failure, and then take the square root, because that's how we do standard deviations, is we root things. Okay, let's look at an example of this, because I feel like I've made it look a little bit more complicated than it actually is. Oh, that example came up really nice. So suppose you're playing a game where there's a 10% chance you will win. You decide you'll only play the game 5 times and then quit, because you want to make sure you cut your losses on that one. Find the probability that you will not win any of the games. So I have nothing but failures, so no successes and 5 failures. So pay attention to those exponents. 0 successes, 0.10 times 0, and then 5 losses. Notice there's no number in front right here, and that's because there's only one way this can happen. Fail, 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 fail. Only one way. So really, if you want, you could put a 1 there, but that's not going to do anything. Okay. You will win the first game, but lose the final 4 games. Okay. So this looks like success and then 4 failures. I'm hoping you notice that these first 2 examples don't really look like a binomial. You could use the binomial to do them though. So 1 success, 4 failures, nothing new yet. Here's where you want to use the binomial. You'll win exactly 1 of the 5 games. So 1 out of 5. Notice this is very different from the previous question. You win the first one. It talks about position. Binomials don't talk about position. They talk about at least, at most, 1 in 3, 2 in 4, things like that. 1 out of 5. So it's not just this first option where you succeed the first try. You could succeed the second try, or the third try, or the 4th try. If you're wondering why I'm writing all these, there's a reason. Or the 5th try. Okay, too many. Ready? Aha! Okay. 1 success, 4 losses, number of ways it could have happened. That's why I did these. Notice there's 5 ways. Okay. If you're dealing with anything other than 1 try out of a certain number, that count the number of ways it could happen is very hard. Rely on a calculator or Minitab to do it for you. You don't want to write out like the number of 2 successes that you could have in 5 tries. It's ridiculously enormous. Don't think it's 10 because it's 100% not 10. It's much bigger. It's like 34. No, wait, 24. 24. Don't write them all out. You just don't want to. Okay. Let's do another example. A tennis player makes a successful serve 67% of the time. That's actually really good. Did I take this from a real player? I don't know. I'm using too many sports examples. Of the first 6 serves in his next match, what model should we use to determine the probability of all his first 6 rounds in play will be in bounds? What's the probability that all of his 6 serves will be in bounds? What's the probability that how many first serves can be expected to be in bounds? So this is a little bit of a different question. So if you look at this, I'm like, oh, I'm trying exactly 6 times. I know how many trials I have. This looks Bernoulli. This is definitely Bernoulli because there's a fixed number of trials. So since I know I'm only going to do 6 serves, bam, Bernoulli. Okay, what's the probability that all 6 serves will be in bounds? So I'm going to use the probability that my number of trials that are successful out of 6 is 6. Here's what that looks like. So again, with Bernoulli, you're counting the number of successes in a certain number of trials. That's why it's x equals 6, not because it's 6 tries, but because we want to know he's successful all 6 serves. Anyway, here's what the model looks like. You can calculate that. Fun times. Okay, the last question we have is, hey, how should we expect this to be in bounds? And there's that hot topic word that we've been dealing with. Expect. How many do I expect? Well, I expect the average. I expect the mean. Oh, it's the mean. It's the expected value. So I just do n times b. So 6 tries, the probability of success is 0.67, so I should expect about 4. 4.02. So if I'm going to try 6 times, I should expect about 4. A little bit more than 4. All right. What should we be watching out for? These are still just models. And when you think model, I want you to think like the models you see in the real world. They're idealistic versions of things. They're not perfect, okay? So although models are good at representing situations, when it comes to real world situations, they'll only give you an idea of what could happen or what it could look like, not necessarily what the truth is in all the world, just so you know. If you choose the wrong model, then everything you will do will be wrong. Watch out for variables that aren't independent because you shouldn't be using independent probability distributions for them in general. You know, be careful. Don't forget that variances of independent random variables, you shouldn't be, you can add, but your standard deviations, you can't. You need the root of the sum of the variances. Be careful with your formulas when it comes to that. So be thinking back to my examples where I was adding variables together and multiplying variables and then adding constants. These are super weird. Make sure you have Bernoulli trials, especially if you're going to be doing the binomial or the geometric, because they use Bernoulli trials to do all of those. The uniform, not so much. Okay, so what have we learned? Hey, we learned about the difference between discrete and continuous. Your first couple of questions in your homework are about those, so make sure you understand the difference between the two of them. The other thing is we learned how to calculate the mean and the standard deviation. Those can get a little complicated, but you know what they are, so we're good. What else did we learn? Hey, we talked about shifting, scaling random variables, so multiplying by a constant and adding. We talked about adding together 2 random variables to see what's going on. And then we talked about the binomial, geometric, and uniform. And I say Poisson on here, but we did not do the Poisson. So just a reminder, no Poisson for you today. Le Poisson, hee hee hee, ha ha ha. It's from The Little Mermaid. It's literally the fish. We're going to do Poisson next time, so look forward to that. Yep. Along with my favorite distribution, the normal. I wish I had a catchy catchphrase to end this with, but don't. Bye!